Okay, in the second half of the t-test module, I want to talk with you about strength of association. We want to predict or explain variation in behavior in psychology, and we'd like to be able to do a good job at that. And so statistical significance tells us something about that, but not that much. So what we'd like to be able to say is some quantitative index of how closely connected our independent and dependent variables are. So how good a job does our independent variable do in changing the dependent variable? So there are a number of statistical indices of this. These are called effect sizes, and common ones include omega squared for analysis of variance, D, Cohen's D, and R, Pearson's R for single independent variables, and R square for a lot of models. So when we do regression models and a lot of analysis of variance models, we can also talk about R square. I'm going to show you first omega squared. This is the symbol for omega squared. And it says the variance in y minus the variance in y given x, so this is a conditional, over the variance in y. And that's equal to the mean of the first group minus the mean of the second group squared over 4 times the variance in y. So these are not really intuitively obvious formulas, but the idea is, if we have two groups, if we have a strong independent variable, we should see a big difference in the means of the groups. And the big difference is sort of the yardstick is the variance of the population. All right, so try and make that a little bit more accessible. The variance in y minus the variance in y given x, the variance in y, or mean 1 minus mean 2 squared over 4 times the variance. So let's say that this guy on the left is our control group, and stop that. and these are the observations in that control group. And now we're going to have an experimental group that could either look like this or could look like this. Right? So what is the variance in y given x? Well, that is the variance in y when x is constant, so it's a within group variance. So if we look at these two groups, the variance in y is the variance of everybody, and if we subtract the variance of y given x, that's the variance within. And you can see the variance overall, if we subtract the variance within from that total, it's going to be a rather small number, and it's going to be divided by the grand total there. All right. Whereas if we compare the control group to this group, this experimental group, the y given x would be the same, but the total variance of y here is going to be quite a bit different, or bigger. And here, if we look at the difference in means, mu1 minus mu2 squared, so here's 1 and 2. Here it's not that very big a difference. And 1 versus 2 here, it's a much bigger difference. So the effect size, when we compare the control group versus this experimental group, is going to be smaller than the effect size when we compare this control versus this experimental group. All right, so when we're talking about T or analysis of variance, what we're talking about is how much of the total variance is explained by the group differences. So we get the total variance and we subtract out the within group variance, and then that's one index of it. Or we just look at the difference in means, how big those are. That gives us another index of it. Okay, so as mean difference gets big, so does variance accounted for. This is something that's widely misunderstood, and so you really need to understand it, and it will help you if you do, and you will find that people in various and sundry places along your career path will misunderstand it, and you won't. So you'll be in a position to make the correct call and perhaps correct them in a very kind and helpful way. Okay, power increases with association, so that's the effect size, and power increases with sample size. So you have a big effect, strong correlation, big difference in means, that helps your power. We have a lot of people, that helps your power. One effect size that is commonly used is D, or Cohen's D, and that's defined as the difference in the means between the two groups divided by the pooled standard deviation. So this is like a z-score, right? Here's your pooled standard deviation. So the pooled standard deviation would be, you know, the average of these. Each one of these has a standard deviation to it, and the pooled is the average essentially of those. So how big is the mean difference where the yardstick is the pooled standard deviation? It's like a z-score. All right. So now for testing significance, you get this effect size and you multiply it by the sample size. So whatever the effect size is, for significance testing, you essentially multiply it by the sample size. So here's the independent samples T, difference in means over the variance pooled times 1 over the n1 plus 1 over n2. So we're going to take, if we just take the square, if we never mind this part, okay, get rid of the sample size, just take the square root of the variance here, you have x1 and x2 over sigma p, and that's the same thing as this. All right, so t here is what you would have for t here if you got rid of the sample sizes here. Okay, so if you just look at the single sample formula, that's, you know, x bar minus mu, so there's the difference in means. And here you've got that same square root. So if we take the square root of this guy, it's sigma, right? So there's your t. And now you're going to divide that by the square root of n. So it's, since you're dividing down here, it's same thing as multiplying. So t is d, the effect size, times square root of n. And you get it here, and you get it here. So the significance testing, the theoretical distribution of the significance test, you get from the effect size times the sample size, and that's what you see here. So the misunderstanding that people have is that because it's easy to get significance with a large sample size, and because big effect sizes give you significance, then it means that if you increase your sample size, your effect size must be getting bigger. So people think that if you get a bigger sample size, you get a bigger effect size. But no, that's not true. The effect size doesn't change at all depending on the sample size. The value of t changes and your power changes because the effect size gets multiplied by the sample size. And so when you get a big sample, you get a significant result, not because the effect size is big, but because the test statistic is big, because you went through and you got a smaller and smaller standard error. So here, this is not the standard error, this is the standard deviation. This is the standard deviation divided by square root of n. All right, so power will increase with a bigger association or effect size and with a bigger sample size. Here's some examples of different effect sizes taken from the educational, what do you call this, the Psych learning outcomes literature. And some of these are all reported in D, the standardized mean difference, but some of them are converted from correlations. It turns out that there's a mathematical relationship between R, the correlation coefficient, and D, the standardized mean difference. So some of these really big ones are actually converted R. So what you're looking at here is student achievement. So what's related to student achievement? Well, teacher estimates of achievement and measured student achievement are really a really big effect size or really high correlation. The effect size is 1.62. You won't get a 1.62 effect size in any study that you do. This is a correlation coefficient that's converted. So teacher estimates of how well students do and how well students do are highly correlated, and that's really not much of a surprise. So self-reported grades. So if you ask students how well they do, and then you look up the records, and they tend to be pretty reasonably correlated. Although the teachers actually have a better idea than the students do, or that may not be true. Actually, it may just be that you're asking them to self-report, and they may not be telling you candidly what their grades are. All right, well, let's look at some things that look like interventions. So giving people feedback results in better performance. So there's a D of 0.7. That's big. Creativity, self-questioning. So if you get people to ask themselves questions about the material, they do better, 0.6. Concept mapping, 0.6. Time on task, point. So these are things that are related to achievement. Some things that really don't. Perceptual motor programs. Single-sex schools tend to not show much of an effect. Gender and achievement shows not much of an effect. Sleep, whole language, types of testing, college halls of residence, parental employment. I'm guessing computer-aided instruction and distance ed. So these are things that basically have no effect on student achievement. So this will give you some idea about possible effect sizes. If you happen to see other tables like this in different domains, please share them with me. I'd like to have a bigger collection than what I have got. I've seen some before and then I've not been able to find them again. So thanks. All right, estimating power. So you want to have enough people in your study so that you can detect the effect that you believe is there. Typically, you don't do a study unless you think you're going to get an effect. And so what you want to do is get the right number of people in your study. If you're going through a grant, then they want to have enough people to get the result, but they don't want to spend any extra money. So you want to power your study, that is, get the right number of participants and everything so that it will come out. Okay, so when the null is true, the outcome will be distributed as t. But if the null is false, then the statistic, the difference in means over the standard error of the difference in means, that statistic t, won't be distributed as t as we know and love it, the short fat relative of z, the normal. Instead, it'll be distributed as non-central t. So I've got some examples here in this graph of what non-central t looks like. And so the shape changes depending on the degrees of freedom. You can see that you got the shape here that's the same on the back side, but it's flattened out on the top side. So here Here we have a non-centrality parameter of 2, and this is basically the idea that the truth in the population is there's a mean difference of 2. And so instead of 0, it's cranked up here. And so with 1 degree of freedom, you'd get this ugly result, and with 5 and with 10, you get the purple line. You notice that that's actually, with 10 degrees of freedom, it's starting to look pretty much like T. It's not so bad. And so if you've got a lot of people, the non-centrality isn't going to be much of an issue. But I'm going to show you how to do the power computations, because you're going to want to do it right. If you do it wrong, your reviewers will complain and you'll feel bad. So, all right. Howell introduces the non-centrality parameter delta for estimating power. For the one sample t, delta is equal to d times the square root of n. That should look familiar. Recall relations between t and d on the earlier slide, so that's why it should look familiar. All right, suppose, and this comes from Howell, that we have 25 people, sample mean of 105, hypothesized mean and standard deviation of 115 respectively. All right. Then if we did this study, we get a D of 105 minus 100 over 15. That's 5 over 15, which is 1/3, which is 0.33. So that's a medium-sized value of D. Delta is D times the square root of n. Whoops. So that would be 0.33 times 5 is 1.65. And now you can go to Howell has an appendix where delta is related to power. If you pick power 0.8, which is the conventional power for psychological research, power 0.8 is what people typically shoot for. You know, here again, there's no magic, but it's kind of like 0.5. 0.5 is conventional, 0.8 is conventional for power. We set alpha to 0.05, then delta needs to be 2.8. So, well, 2.8, we didn't get there. And it turns out that power in this case is about 0.38. Now, you wanted 0.8. 0.38 is really crappy. That means that out of 100, if you did this study 100 times, you'd expect to get a significant difference 38 out of 100 times, so less than half. Well, all right, we want 0.8. So to solve for n, we would need delta over d squared, 2.8 over 0.33 squared, 8.48 squared, about 72 people. Dependent t, you want to turn that into a single sample t using different scores. And so that's same as this. For the independent t, to use Howell's method, result is that he gives you as n per group, so you have to double it. So, for example, if d is 0.5, we got a mean effect, and n is 25 per group, then delta is d times square root of n over 2, 0.50, that's our effect size, and we get 25 people per group with 2. So 0.5 times square root of 12.5 is 1.77. So we go to the appendix, delta 1.77, alpha 0.5. That's a power of 0.3. That's not so good. For 0.8, we need a delta of 2.8. And so we go through this business again. And in this case, we would need 63 people per group. And here's SAS Proc Power. I kept SAS for this. I used package R for everything. The reason I'm using SAS for this is it's quite good and it's pretty easy. So you don't have to learn any of the SAS syntax. All you have to do is call up SAS and then type these lines in here and tell it to run. So that's good. It's easy. So you say proc power because that means that you want SAS to compute power for you. And if you're doing t-test, you have one sample means test equals t. So I'm going to do this the single sample chubby do. We had the null mean is 100. The observed mean is 105. Standard deviation is 15. Power we want is 0.8, and in total, the missing value for SAS is this period, so you put period, and SAS is told that you're at the end of the line when there's a semicolon. So this says, I want proc power. Here's the analysis that I want. Here's the givens. Here's what I want you to compute for me. I need to know the total n. Run says to compute these things. So I will select this and tell SAS to run. And when it does, it comes back and tells me this. So here's the input, and here is the output. Power procedure, one sample t-test for the mean, fixed scenario elements, distribution is normal, method exact, so this is an exact method of probability computation. Null mean is 100, the observed mean is 105, standard deviation is 15, nominal power I want is 0.8, number of sides, so this is alpha is two-sided here. Alpha is set to 0.5, so these things you can change if you want, but typically you don't. Computed total n says a power of 802 with an n of 73. So we had 72 here, so close enough. All right, and I trust this. This if you tell your reviewer for your grant that you did this with SAS, they will believe you. Okay, two sample t power. So here again, I say proc power. Now I say two sample means. I have a mean difference of 0.5. I have a standard deviation of 1. I have power of 0.8. How many people do I need? All right, well, it says two sample t-test for mean difference, blah, 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 same stuff. Mean difference is 0.5, standard deviation is 1. This is a d of 0.5. Okay, so you can take any mean and any standard deviation and change it into a value of d by making the standard deviation 1 and telling it the d value. So this is a d of 0.5. I want a power of 0.8. I want a two-sided test. I want assumed null difference is 0, which is the usual case. Alpha set is 0.5. I weight the two means equally. It says I need, for a power of 0.801, I need 128. So what's that, 64 per group. All right, and here it says 63. So here's our d of 0.5. All right, so 64, I would say, is about right. 63 is, within shouting distance. Okay, so that's how you use SAS to get those power computations. Two sample t power. So what have I done here? Oh, okay, so I'm asking it to tell me power instead of sample size. So usually you want to you're trying to figure out the sample sizes, but in this case I'm trying to figure out the power. So I've got two samples. I got a mean difference of 5. I got a standard deviation of 10. I got a one tail. I got total people 25 per group. I want to know what the power is. And it says okay. Here's I got a one-sided test. I got a mean difference of 5, a standard deviation of 10, total sample size 50, null difference 0, alpha is 0.5. Computer power is 0.54. Not too good. All right, so I can use this to ask SAS to tell me about power in typical studies in psychology. So I've done a number of meta-analyses, and there are meta-analyses where they just go across all areas of psychology and they say, what's the effect size in D when we're doing these kinds of studies where we compare means. And typically in psychology, the overall average is about 0.4. And so we want to think about power when the effect size is somewhere between 0.3 and 0.6. So if it's much less than 0.3, you should choose a different topic. If it's much more than 0.6, 0.7, 0.8, when you're getting up to 0.6, it's hard to find things bigger than this where it's interesting psychologically. So you can get effect sizes that are 1, which are a whole standard deviation difference, but these are things that are so blindingly obvious that nobody does them. So as I said, by convention, the power 0.8, and if we look at somewhere between 0.3 and 0.6, the power 0.8 what do we need for sample size? All right, so 2 sample test for if our effect size is 0.3 and the power we want is 0.8, then we need 352 people. If it's 0.4, we need 200. Now this is the typical sample size. I'm sorry, effect size in psychology. So if you're doing a t-test, you probably want to have 100 people in each group. If it's 0.5, now you need 128. If it's 0.6, now you need 90, so that's 45 in each group. Now people, for a 0.8, people are doing, about 50 people per group or 25 people per group. If it's 25 people per group, you're not going to have a good power even if you have a really big effect size. If it's 50 people per group, you now have adequate power if you have a big effect size of 0.6. So this is the graph that relates the power of the test to the sample size. So for a 0.3 effect size, so this is not really small. That's a correlation coefficient of about 0.15. To get a significant difference, you're going to need about 200 people here for the 0.5. I'm sorry, wait a minute. 0.3 power. Oh, power is 0.5 with a little less than 200 people. For a 0.3, we need a lot of people. 350. Okay. So my advisor, well, one of my teachers in grad school said his advisor told him, study the whoppers. What does that mean, study the whopper? Well, what he meant was you're an experimental psychologist and you're going to be doing experiments, and the things that you use for your independent variable should have a whopper of an effect, a large effect on the dependent variable, which means a big effect size. And the reason he told him that is if you have this nice big effect size, then with the kind of sample sizes that we get in psychology, like 100 or 50, then you are going to have good power, and your results of your studies are going to come out. They're going to be significant, and you're going to be smiling after spending 6 months to a year on this project. Whereas if you study these subtle, nuanced things, these theoretical advances that are esoteric or they're theoretically important, but they don't show a big increment, then you better have these enormous sample sizes, and probably you won't. And so probably what will happen is you'll get a non-significant result for your study, and then you'll be weeping about the 6 months or a year that you spent on whatever it was that you were doing. So go for the whoppers. All right, so I want you to figure out about how many people will you need for a power of 0.8 if alpha is 0.5, 2 tails, and you have an effect size of 0.3. You can only afford 40 people per group, and based on the literature, you estimate group means to be 50 and 60 with a standard deviation of 20. What's your power estimate? So this one you can just sort of look up on the slides that I did already. This one you can plug into SAS and with the information I gave you and figure out what the answer is. All right.